Let us come to rectangular fin, its heat transfer analysis. Rectangular fin heat transfer analysis. In many industrial systems such as industrial furnaces, the IC engine which is utilized in the bikes and the automobiles like car etc., where the internal combustion engine is heated up to a certain extent of temperature. So, in those cases it is impossible to remove the heat energy from there. So, technologists were think over in this direction that how such type of heat energy can be removed from the machine part which is used in the automobile, for which a direct removal of heat is not possible. So, if you consider the Fourier law of heat conduction, then you can easily emphasize the fact that the area from which the heat energy is being receding to the environment has played a major role in order to dissipate the heat energy. So, in the design itself, what is done, a certain the area from which heat is to be removed is increased by utilizing the fin or extra projection on that particular machine part. So, rather than a conduction system, a conduction convection system is being imposed in such type of circumstances. That means, the heat energy which is conducted by the material of this equipment needs to be convected to the ambient air by the convection mode. So, such type of cases are also known as the conduction convection system. So, in the present class today, we will try to understand the heat transfer analysis in the rectangular fin. Let us take the example of a rectangular fin as shown in this figure. This is the rectangular fin. This is the length of the fin measured in a direction parallel to the heat flow direction. This is your width, this is your length, or this is also called the height of the fin. This is your width W. Sorry. Please, needs to be shown here in the isometric view. Let us try to show in the isometric view. So, in this manner, so that it looks like a three-dimensional object. So, this distance is the W. This is also called the width of the fin. This is called W, and this is the thickness of the fin, that is, let it be 2 delta. This is the So, a rectangular fin has been shown in this diagram having length L, the width W and the thickness 2 delta. Here the the heat energy is being receded by this surface. So, let us suppose this is an infinitesimal area or infinitesimal section under consideration in order to set up the differential equation for the present case. Let us suppose an elementary section has been taken at a distance x from the fin base. This is your fin base, this is the L which is measured as in the direction parallel to the heat flow direction. This is the width W which is measured perpendicular to the direction of heat flow, and this is the 2 delta, that is the thickness of the fin. So, in the formulation of the problem you can write here, let us consider a rectangular fin. Let us consider a rectangular fin of length L, also called as fin height, width W and thickness 2 delta. This is the root of the fin, this is the fin root, and we have to conduct the heat flow analysis, for the present case, So, this is all about the formulation of the problem. This is the fin, that means the extra area which has been projected in order to remove the heat energy which has been generated, and you have to set up a differential equation for this case, and applying the boundary condition you will have to arrive at the exact solution of this heat transfer problem, and from there we can infer some of the important conclusion which is of immense importance in the fin design. So, the first task is setting up of differential equation, for the case. So, let the thickness is delta x. Let us assume a representative fin portion at a distance x, from the fin root and of width delta x. So, when we consider this, so what will happen? So, this distance is x, this distance is the q, this distance is x plus delta x. So, we can write, that is the qx, that is heat conducted at x is equal to x. How much that should be equal to? According to the Fourier law, that should, this is your profile area. Let us suppose this is your profile area, and this is, when you cut this, So, this area that will be the cross sectional area. So, this will be your cross sectional area AC in the plane of the blackboard, this area. So, the heat conducted at x is equal to x, that will be how much? That will be equal to minus k into the cross sectional area into dt upon dx. Now, let us suppose that I am cutting this rectangular fin at this section. So, this much area will get exposed to the environment. So, if at this point, if I am considering the heat convected at area at x is equal to x, that is the heat convected at x is equal to x. So, that will be equal to how much? This area is equal to how much? That is the perimeter into delta x. That means W, assume this has been cut, perpendicular to this line, perpendicular to the fin direction. We have made line. Then area that will be equal to, that is the perimeter into the thickness into the convective heat transfer coefficient H into T, that is the temperature of the fin minus temperature of the atmosphere. So, for steady state heat flow, what should be the condition? That the heat convected at x is equal to x minus heat convected at x is equal to x, that should be equal to heat convected through this area x plus delta x. So, that will be equal to q x plus delta x. This q x plus delta x, if you apply the Taylor series here, then this can be expanded as this. So, QC, that should be equal to minus day by qx by day by x into delta x. So, the expression for QC is P into delta x into H into T minus Ta, that should be equal to, take the differential coefficient of this quantity. So, we will get minus k into AC, these are the constant quantity, d2t upon dx2 into delta x. This delta x will cancel out, or pH into T minus Ta, that should be equal to this minus and this minus, this will get plus, that will be equal to k into AC into d2t upon dx2. So, the differential equation for the present case comes as d2t by dx2 minus pH upon KAC into T minus Ta, that should be equal to 0. This is the differential equation for the rectangular fin under consideration. Now, you have to make certain substitution in that for further analysis. So, let us make the substitution that the T minus Ta is equal to theta, that is the theta is known as temperature difference. Now, let us make the substitution. Let us make the substitution T minus Ta, that is equal to theta. So, Ta is constant quantity. So, dt upon dx, that should be equal to d theta upon dx. So, taking the second derivative d2t by dx2, that is equal to d2 theta by dx2. Thus, the differential equation above can be reproduced as d2t by dx2, that may be converted into d2 theta upon dx2 minus ph by kac theta is equal to 0, or we can write d2 theta upon dx2 minus m square theta is equal to 0. Let it be the equation number 1, which is the differential equation for the present case, where this m square is equal to pH upon KAC. So, in order to analyze the heat flow behavior in this rectangular fin, differential equation number 1 needs to be solved by the help of the pertaining boundary condition in the case. So, let us visualize what the boundary conditions are. So, the boundary condition for the present case, boundary conditions for the present case are: number A, T is equal to T0. Let us suppose the temperature of the fin at the root, that is this is the root, is T0, that is at x is equal to 0, So, when we transform this equation as per our assumption that the T minus T is equal to theta, we can write imply that T minus Ta subtracting the same quantity T naught minus Ta at x is equal to 0. So, we can write theta is equal to theta naught at x is equal to 0. This will be your transformed boundary condition as per the substitution made earlier, and the second boundary condition should be heat conducted through the area AC, that should be equal to heat convected from area AC, is it not? At which point? At x is equal to L, because whatever the heat energy that has been conducted through this film material, all that amount of energy needs to be convected to the environment through the convective mode. So, what I am saying that the heat conducted through the area AC, that should be equal to the amount of heat energy which is convected by this free end, that is from the area AC, that is the cross sectional area, which can be assumed perpendicular to the heat flow direction. So, at x is equal to L. So, this is your second condition. So, these are the two boundary conditions, and this is the equation number 1. These two boundary conditions and the equation number 1 need to be kept in mind throughout the entire derivation of the present class. So, the solution of the equation number 1 can be seen if you see the auxiliary equation for the differential equation number 1. So, auxiliary equation for differential equation 1 is d square minus m square, that should be equal to 0, or d is equal to plus minus m. So, the solution of equation number 1 is of the form, because you have set up the differential equation in terms of theta, that is the temperature difference. So, the solution will come in also in the form of temperature difference. So, theta that should be equal to A e raised to the power m x plus b e raised to the power m x. So, in terms of hyperbolic function, e to the power m x can be written as cos h m x plus sin h m x plus b cos h m x minus sin h m x. That can be further written as a plus b cos h m x plus a minus b sin h m x. That can be written as c1 cos h m x plus c2 sin h m x. Let it be question number 2. Now, the next task in front of ourselves to evaluate the integration constant C1 and C2 from the existing boundary condition for the present case. So, taking the condition number 1, taking the condition number 1, condition number A. So, take the reference equation number 2 plus boundary condition number A, that means theta is equal to theta 0 at x is equal to 0. So, the theta 0 that should be equal to C1 cos h m x at x is equal to 0, that is 1, plus C2 sin h m into 0, that will be sin 0 0. So, that is equal to C1. So, the value of first integration constant is C1 is equal to theta 0. Let it be question number 3. So, the expression for theta comes as, theta naught cos h m x plus C2 sin h m x. Okay. So, d theta upon dx m theta 0 sin h m x plus m C2 cos h m x. So, taking the condition, this one, that is the heat conducted from through the area AC, that should be equal to heat convected. Now, taking the boundary condition B in view. So, according to B, what we can say? Now, the boundary condition B, it needs to be evaluated in terms of mathematical terms. So, heat conducted through the area AC, that is equal to K into AC into d theta by dx at x is equal to L, that should be equal to H into AC into theta, that is the temperature difference at x is equal to L, or you can say minus k into AC will get cancelled out, minus k into d theta by dx at x is equal to L. So, that will be equal to m theta 0 sin HML plus m C2 cos HML, that should be equal to minus h theta at x is equal to L, that is equal to theta 0 cos HML plus C2 sin HML. This will give you the value of C2 as, now these things can be removed. So, we can write minus m k theta 0 sin HML, and this term containing C2 should be, I am transposing it to the right hand side. So, this quantity here minus sign will not be there, sorry, that is plus s theta 0 at this. So, bring that h theta naught cos HML on the left hand side. All these terms does not contain any C2 term. Now, transposing the C2 terms on the right hand side, that should be equal to m k C2 cos HML plus h C2 sin HML. So, we can write minus theta naught m k sin HML plus h cos HML, that should be equal to C2 m k cos HML plus h sin HML. From there, the value of the second integration constant arrives as minus theta 0 m k sin HML plus h cos HML divided by m k cos HML plus h sin HML. So, let it be equation number 4. So, the complete solution for the temperature difference or the theta as it appears in the present case can be given as, thus the complete solution can be given as, let us try to proceed from here, here it has been given, only the value of C2 needs to be incorporated in this case. So, let us proceed from here, that is equal to theta 0 cos HMX plus, that will be minus theta 0 m k sin HML plus h cos HML divided by m k cos HML plus h sin HML. So, this is your expression for the theta, that is the temperature difference. Now, or further you can transform here, that is equal to theta 0 cos HMX minus theta 0 MK sin HML dividing the whole expression in numerator and denominator by H cos HML. So, that is equal to 1 plus MK upon H plus this will be 10 HML, that is the dividing the numerator and denominator, each and every term of numerator and denominator by this term H cos HML, this. So, solution comes as theta equal to theta 0 cos HMX minus theta 0 MK upon H 10 HML plus 1 divided by MK upon H plus 10 HML. So, this equation and this equation are collectively called as equation number 5. This equation number 5, it is a solution of equation number 1, which gives the idea about the temperature distribution in a rectangular fin during its heat flow. Now, the next task is, what is the amount of heat energy which has been lost by the fin during this arrangement. So, let us try to derive the expression for the heat loss. Keep this equation, equation number 5. Thus matter heat lost by the fin, that should be equal to minus k into AC into d theta by dx at x is equal to L, sorry, x is equal to 0 at the root, that should be equal to this much at x equal to 0. So, this is the expression for theta. So, the d theta by dx may be given as m theta 0 sin HMX minus one term has been missed in this equation number this is the value of the integration constant C2. So, this needs to be multiplied with sin HMX, sorry. You should incorporate this term sin HMX in the previous equation to this also. That means, theta is equal to theta 0 cos HMX minus theta 0 into MK sin HML plus H cos HML divided by MK cos HML plus H sin HML into this sin HMX. Please rectify that equation. Sin MK has missed from my side. So, that will be equal to MK upon H, this is a constant quantity, 10 HML plus 1 divided by MK by H plus 10 HML into the differential coefficient of this, that is m cos HMX. Okay. So, the value of d theta by dx at x equal to 0. So, this will be 0, that is equal to minus mk upon h 10 HML plus 1 divided by mk upon h plus 10 HML into m, and this value equal to 1. So, the heat lost by the fin, that is equal to Q, that is equal to. So, the expression for Q comes as, Q is equal to, because that needs to be a positive quantity all the time. So, minus minus plus here also it is coming plus KACM here theta 0, this is the term also, this is missing, theta 0 into m theta 0. So, KACM theta 0 into mk upon h 10 HML plus 1. Please look in the equation number 5 also, that whether theta 0 is missing there, or if it is missing then get it corrected, divided by mk upon h plus 10 HML. So, this is the expression for the quantity of heat energy which is losing from the fin. Expression for heat lost. In equation number 6, this is also called a desired solution of the equation number 1. This is also called the desired solution of equation number 1, because for engineering purposes, if you are not knowing the quantity of heat energy which is being dissipated by the virtue of fin, it is of no importance. So, the equation number 6 has the relevance in order to establish that how much quantity of heat energy will be lost by the applying the fin to a surface. So, now consider two small cases, that the evaluation of m square, that is m square equal to pH upon KAC. At present case, the Kp, that is equal to 2 W plus 2 delta into H divided by K into AC cross sectional area, that is, this is the cross sectional area. So, length into this height, that is the width here, K into W into 2 delta. So, that will be given as 2 W plus 4 delta into H divided by 2 W into K into delta. Since the quantity 2 W is much greater than 4 delta, hence as an approximation we can write 2 W plus 4 delta is nearly equal to 2 W. So, the expression for m square comes as 2 W into H divided by 2 W into K delta, that is equal to H upon K delta. So, the evaluation of m, that will come as H upon K delta under root. Similarly, for a fin having circular cross section, so if the cross sectional fin, if a circular cross section fin is there, then the value of m square will come as P equal to 2 pi r into pi d into H divided by K into the cross sectional area pi d square by 4. So, this is pi d, this will get cancelled out. So, the 4 H upon K d. So, in this case the value of m is equal to 4 H upon K d raised to the power half. These formulas should be kept in mind for solving the numerical problems. So, in the next class we will see the special cases of this rectangular fin, that what will happen if the length of this fin is infinite, and also the second one is this extreme end is fully insulated, how the boundary condition changes in those cases, and how the solution of fin will get changed, that will be seen in the next class. Thank you.